Second. Also, that voice is crazy. Okay, so welcome everybody to one of the last, actually, I think the last deep learning theory seminar of the formal semester, but still going to go on in the summer. So today we have the honor of having Mary Letey. So Mary is doing her PhD in Harvard. I guess we met at NeurIPS, talking about physics and geometry. So this is what she does. She does the physics and the geometry. I do the geometry. So Mary's doing her PhD with Cengiz Pehleman. I can't say his name properly, but I'm sure you can correct. And so it's in Harvard. And before she did her master's in the Pretrained Institute in Canada. And she'll be talking about, I think, one of the most relevant topics actually in, I guess, modern machine learning. So it's like in context learning, and she'll be specifically focusing on linear regression, via linear attention mechanisms. So after you, actually.
Thank you so much. And yeah, thanks everyone for joining. It's going to be a fun one, I hope. So yeah, I'll be talking about our paper, which is titled Theory of In-Context Learning, or an asymptotic theory of in-context learning of linear regression using linear attention. So this is going to be, to give away the spoiler, we'll develop some tractable model analytically of some in-context learning phenomena with a regression problem solved by a linear attention mechanism. And we can solve everything about it analytically using random matrix theory, statistical physics style computations. And then we can say some things that are not only true for this linear attention, very toy case, but also true empirically in more interesting architectures. So I think it's a nice toy model to dig our teeth into. And yeah, I'm a second year student at Harvard, and this work was done in collaboration with my amazing co-authors. So we've got Yue, Cengiz, Anindita, and Jacob, and then yeah, done at Harvard with the Kempner Institute and with KITP Physics. So lots of good people. Cool. So the structure of this, I'll just introduce, I'm sure we've all heard like Juno just presented about in-context learning a few months ago. So I'll just give the initial spiel about why we're interested in this and what questions are interesting. And then I'll pivot more to the specific regression task that we're going to look at, and how we're going to target it specifically with linear attention, which makes it analytically solvable. Then we'll present like results about what the analytical solution is and talk a little bit about the derivation, how this is done. And then I have three stories about interesting phenomena that appear as derived from the linear theory, but also hold in nonlinear architectures. And then we'll see where we can go from there. So yeah, as an introduction, like we're all, I think, familiar with the idea of in-context learning, which is when large language models, sequence models, like these big, models that we may not understand perfectly, seem to be able to execute a new task, having conditioned only on some information about this task, maybe examples or some prompting seen in an input, where this execution of the task, this learning of the task, this inference is done without gradient updates or without weight updates. So it's somehow gradient-free learning. It's learning some implicit algorithm to transform a given context and given examples into inference, which is very cool. And there's lots of interesting things we could say about this. I think the most familiar example of this maybe is the case of natural language processing. So for example, here's an example of English to Klingon translation where my GPT was probably not trained to do this, but maybe it's seen some examples of Klingon text in the internet corpus and it's seen lots of examples of English in the internet corpus. And so in context, it somehow comes up with some algorithm where if I give it a prompt, so my prompt is going to be all these input-output pairings of English to Klingon, and then I query it with a new English word, it will give me the Klingon word, hopefully. And this has been observed, like there's been lots of studies of like NLP natural language in context learning for translation or whatever that occurs and emerges in large language models. Language is a very complex structure, and large language models are these big, crazy things. So this may not be the easiest playground for a theorist, but it still evokes a lot of interesting questions. For example, like we don't really know what causes this ability to emerge. We have some ideas. People talk about pre-training distribution and burstiness and power law structure and all these really interesting things, but do we have like a very concrete description of what causes in context learning to emerge? What's the dependence on architecture for a given task? How is the task structure important? What's the data sufficiency? What's the sample complexity? What can we say about the data quality in addition to data properties? What can we say about runtime? All of these things. So there's a lot of interesting questions, and hopefully I'll convince you by the end of this that we can answer some of them if we go back a step and look at the toy model. So the toy model that we're going to look at, every theorist's favorite playground is regression. So I'm going to, similar to the NLP example, I want to prompt my model with some context. And this context is going to be input-output examples. So it's just pairs of x and some function of x, and another x and some function of the same function of a different input. And I give you a long context of these input-output examples, and then I query you on this XL+1, I've denoted it. And your job as the LLM or as the model is to predict this test label. And what that implies is that you've effectively regressed this function f by seeing these examples of it in this prompt. In my particular case, I'm not going to do just a general regression, I want to do a linear regression. So I make f a linear feature that depends linearly on this input token. I give you L examples of this, so L would be the context length here. And then I give you multiple context prompts at pre-training. So I'm not just going to show you one regression problem. I'm also going to pre-train this model on n contexts. So this is just saying the same thing, but with the linear feature encoded. So I'm going to give you a context of length L. This context is going to have the structure of inputs and outputs. These outputs will be linear related. So this label Y is going to be inner product of my token with my task vector W plus some label noise. And you see this task vector W has some index mu. This mu is the context index. So this denotes the fact that we're not just going to see one sample of one regression. We're going to see n samples of n different regressions. And these regressions are unique because they're determined by this W mu task vector. Cool. So this is the structure of the data, very, very loosely. Now, what is the actual architecture? How is this model going to learn this? Is it even possible for this model to learn this problem? We're going to start with the simplest thing that we want to study, properties of LLMs, properties of transformers, but softmax makes things very difficult. So let's just go with linear attention. So a lot of works have studied this in recent years as well. It's a very nice tractable model. So we just look at the linear attention module. It's determined by these parameters like value matrix and key and query matrix. You'll notice that this looks almost exactly like a softmax attention block, except that there would be a softmax wrapped around the KZ transpose QZ term. So this is just exactly regular attention, but without the softmax. Great. And we like this model because it preserves like these quadratic self-interactions between the embedding Z. I haven't yet told you what this embedding is going to be, but it will be something that is dependent on the context and these input-output examples that we see. And we want them to talk to each other because we want them to interact so that we can uncover this linear feature at the end of the day. So this is our linear attention module. Z is a matrix of size token size by sequence size. That's the dimensions. And the output of this attention module will just be another matrix of the same dimensions as Z. Now, Z in our case, we're going to make a design choice where we choose an embedding. So previously I've described that we have these n different contexts. And in each context, we give a sequence of length L. Each element of the sequence is some input-output mapping, some X and some Y. We can structure this in any way that we want. We choose this particular design choice, similar to other papers in the literature. It's a nice stacking, it allows the model to see both the structure of the inputs X and the outputs Y within the same column, which ends up being nice theoretically. So this is the embedding for one particular context. For one context, we take our input-output pairs and we just stack the input and then the output. And we do this for the L input-output pairs. And then at the end of this embedding, we add the query. So this query is highlighted in blue. And that query is the thing that we want to regress. So we want to prompt the model with this XL+1. And then we just fill in the corresponding y value with 0. This is going to eventually be the label that the model will be trained to predict. And again, we're going to have n of these. So this is one embedding for one context, which corresponds to one linear feature, which corresponds to one w mu. So again, this mu index runs from 1 to n. We're going to have n of these z's, which are going to be our embeddings of our contexts. And yeah, as I said, this predicted value, we're going to train the parameters of the value matrix, key, and query. And all that we care about is this final output label, which is going to be in the bottom left, bottom right corner of this matrix after we apply the linear attention to it. So this is going to be our predictor. Now, the first thing that we want to do is actually understand the structure of this predictor. So I can go back to my definition of linear attention. This is my definition right here. And I can plug in the structure of my particular embedding that I've chosen now. So I'll just plug in a Z mu and I'll see what happens. And I define some value matrix. I just write it out in terms of its components. Same for key and query. I just write everything in terms of its components and I unroll this expression. I see what I get. So what I get is I can actually approximate. So this is not exact. This is an approximation. But if I enroll this final element in terms of all the key and the query and the value parameters, and I look at what terms actually tell me something about both the x and the y and the query, because not all terms will attend to everything that's relevant. So I can discard some terms safely. Again, it's an approximation, but I can safely discard some terms. After I discard these terms, I can write this label as just a nice inner product of some parameter matrix gamma and some feature matrix H. And here's what these look like. So gamma, as you can see, is some like slightly off square matrix. It depends on a scalar component of the value matrix, and then particular matrix and particular vector components of the attention matrix, which is K transpose Q. So gamma is effectively the attention matrix scaled a little bit by the value matrix. And again, the reason why not all of the attention matrix appears in here and not all of the value matrix appears in here is because one, we're only looking at the final output term, so we're only really attending to the query. And also there's terms that just don't really contribute, so we can ignore those. We don't need all the parameters in the attention matrix and the value matrix. And then this feature matrix, which is going to be multiplied by this parameter matrix gamma, this H has this structure as shown. So it's going to be some outer product of my query, XL plus 1. And then there's this matrix structure, which is effectively some sample covariance, like it's the label and then the tokens. And then there's also like a sort of a second order quadratic term, this sum over the label squared, which also appears. But the main contribution is this first term. Don't know if I can highlight. Yeah, the main contribution is going to be this first term right here. Do I delete that? Amazing. Okay.
Okay, cool.
Yeah. So this is our structure. And again, this is an approximation, but other people have made this approximation. They've shown that not all of the parameters in these value and attention matrices are relevant at the end of training. So doing empirical studies, not doing theory, but doing some empirical studies, they show that if you initialize the parameters that we ignore close to 0 and then train the model with those close to 0 initialized, they will eventually just converge to 0. So as long as they're not initialized like as something super, super large and you get weird gradient effects, these parameters are empirically effectively ignorable. And here we just do that straight from the bat in the theory. That way we have this nice inner product structure for our label predictor. And this is actually really interesting because maybe a priori we wouldn't know that linear attention can even do this problem, right? Like there's been a lot of discussion about what architectures can actually do in context learning. Do we need softmax? Can MLPs do it? MLPs can do it, but they have to be deep enough, right? There's a certain level of nonlinearity that comes into play. Are linear transformers linear or nonlinear enough? That's the question. It turns out for this case, as we write the predictor in this form, we can kind of get a population level intuition for what this predictor is going to eventually learn. So I highlight this term the term I was trying to circle earlier, because I think this is the leading order contribution, and I think it's the most intuitive term that gives us some insight into what's actually happening. So if we look at this, and if we unroll the fact that Y is just going to be W transpose X, then this term is going to be a sum over W transpose X, X transpose, which is effectively just W times the sample covariance for the tokens X. And so when we look at the structure of this predictor, or sorry, when we look at the structure of this feature matrix, H is going to roughly, I'm forgetting that quadratic sum of Y term at the end, like I'm fudging a bit, but it's going to be roughly this query XL plus 1, my task vector W mu, which so far I haven't told you anything about, and then my token covariance. And my label is going to be the inner product of this matrix with gamma. So if gamma learns to invert this sample token covariance, then all that I'll be left with is the predictor will be the inner product of W mu, which I still haven't said anything about, and XL plus 1, which I still haven't said anything about. So we have a general predictor that's precisely the structure of this linear feature. I haven't given you any information about the task. All I've given you is this feature matrix H. From that, the model learns some approximation of the token covariance. And if the parameter gamma converges to the inverse of that token covariance, then automatically we have a solution. The model will perform the in-context learning exactly. Now, again, I stress that this is a population view because I haven't talked at all about like finite data effects or sample complexity or anything. This is just more intuition, like this architecture could solve the problem. It could. What gamma ends up actually learning is a bit more complicated, but this is just intuition that if gamma were to learn the sample covariance, and if the sample covariance were to be a good estimate of the true covariance, then this in-context learning problem would be solved. Cool. All right, the introduction is nearly there. Yeah, so again, this is just saying something similar about what I've said before. But for now, I'll go on to introducing the parameters that we actually have in this model. So this is going to be the structure of the pre-training data. These are going to be a finite number of contexts, prompts, that I show, which are examples from different lines. So the structure of the X's, the inputs, the tokens, will be sampled IID from some nice isotropic Gaussian with the correct scale. We'll also add on some label noise to each of the labels, which are like linear features plus some label noise. And these will be another nice IID Gaussian. And then the tasks, so these are the regression vectors. These are what determine the functions that we're learning in context. These will be chosen uniformly from some finite set of a limited number of tasks. So we're going to take our normal distribution. We're going to sample k tasks, only k. And then as we sample our contexts, again, there are n contexts, we're just going to only choose tasks from these previously selected k tasks. The reason for this is because, spoiler alert, I want to eventually limit the data diversity in some meaningful way. I don't want the model at pre-training time to have access to the entire distribution over the function space. Or maybe I do, but I want some way of controlling it. So if k is less than n, then some of the contexts will have repeating functions. They won't have repeating tokens because the x's are sampled independently all the time, but they will be learning the same function. And if k is greater than n, where n is the number of contexts, then effectively each context has a unique function. So we're more broadly sampling the function space. So again, I have 3 parameters for now. I have the context length L. This is the number of input-output pairs. I have N, which is the number of prompts, the number of contexts. And I have K, which is this limited task diversity. How many unique tasks am I actually seeing during pre-training? And again, this is independent of number of contexts. Cool. And then there's going to be 2 distinct tests that I do. So after I train my model, I get my parameters. I want to test it. The prompt will have the exact same structure. It will be a sample of input-output pairs of context length L with some query. The job of the network, which it's been trained to do, is to predict the label for that query with the same embedding structure and everything. The only difference is how I sample my data. So, yes, and of course I should mention how we're actually going to train this. We're going to train this with regression, which will be very nice and analytically tractable. All I'm doing here is an MSE loss over my samples. So I'm ranging my mu index 1 through n, where again, n is the number of contexts. And I'm looking at the error between my true label predictor YL plus 1 and my model predictor, which is this inner product of gamma times my feature matrix H. And I also add some regularization. So that's just the label and then my regularization term. Very nice minimization problem. And then at test time, again, everything has the same structure. It's just the statistics are a little different. So I sample some fresh tokens from the exact same isotropic scaled distribution. My noise has the exact same statistics. And now I test on a general task. That should be the normal distribution with zero mean. It should match the previous one. Yeah. So yeah, this I instead of pre-training, so I pre-train on a limited finite sample of size k. So I'm limiting the number of tasks that I see. At test time, I want to test on a general task because I actually want to probe whether or not this model is learning in context or if it's just learning the training tasks. So the only difference here is that I test on the full task distribution, which is this isotropic Gaussian. Conversely, I also want to probe how well the model is doing on these training tasks. So I wouldn't call this training error because I have different tokens, but I do want to test the same regressions that I saw during pre-training. So for this in-distribution error, I'm going to have the exact same noise profile, the exact same token profile, the exact same embedding structure, everything will be the same, but I'm going to sample my tasks exactly like I sampled them during pre-training. So from this finite set of size k. Awesome. Okay, yeah, that's everything for the introduction and the setup of the problem. So I'll pause briefly if anyone has questions.
For me, it's okay, but anyone in the audience? Audience is always shy, so I guess it's good.
Awesome. Okay. Right. So now we can actually get to the main results. And before I describe these parameters, again, just to summarize, we have four main quantities in this theory. We obviously have the dimension of all of our vectors. So this will be the D. This is the dimension of the tokens. This is the dimension of the task. Then we have L, which is the context length, the number of input-output samples that you see within a given context. We have K, which is the limited diversity, this finite number of tasks that we actually sample during pre-training. And we have N, which is the number of contexts, so the number of prompts that I see. In the view of the model, this N is just the number of data points that it has. Because all the model sees during training is the embedding Z and the output Y corresponding to that embedding. So what we identify, spoiler alert, this will be an asymptotic theory because we like high-dimensional statistics. So we'll be studying these things in a limit where we take a dimension to infinity, and then we try to figure out how to scale these three other quantities that we have in our theory appropriately so that the results make sense. And the first result that we have is we identify the correct scaling for this type of limit that we want to take. So we need the context length L to scale linearly with dimension. We need the task diversity K to scale linearly with dimension. And we also need the number of contexts to scale quadratically with dimension. And the reason for these are, in my opinion, somewhat intuitive. So I'll go through each of them. We start first with alpha. So alpha describes this proportional scaling, linear scaling of context length with dimension. And this is familiar from general ridge regression. So for this problem to be done successfully, I think there's three different views you can take of it. And each of them is important and each of them plays a role, which is why the final answer is going to depend on each of these parameters. The model needs to learn some approximation of the true statistics, the true distribution of the tokens. And we know from ridge regression that if I give you samples from a regression problem, just one prompt, just one sample. Sorry, not one sample, but one set of L samples. The correct scaling here is going to be the number of samples I give you divided by the dimension. Because in order to learn the statistics of my tokens here for this ridge sample, I'm going to need proportional to the dimension of my tokens in order to actually learn the true distribution of those tokens. So alpha here, again, this relates context length to dimension, and this kind of comes from just general ridge regression. How much data do I need? How many samples do I need to do a ridge regression problem to truly estimate the statistical structure of my samples, conditioned on the fact that they're Gaussian? Kappa will be very similar. So kappa, again, instead of taking the token view, kappa describes the the task view. So again, not only do we need to estimate properties of the token distribution, we also eventually want to learn the true function distribution. And the function distribution is equivalent to a Gaussian, because that's how we sample the tasks. But we only see finite samples of the tasks. We only see k of them. And so how well we're estimating the true function distribution or the true task distribution is going to depend on how k scales with d. In order to estimate the mean and the covariance of my task distribution, I need d samples. If d is growing, k needs to be growing linearly. And then finally, there's the third view. So these two previous views were kind of smart in the sense that we're thinking about how we would do this problem as a theorist. But the final view, we just need to think about how would my linear attention do this problem. All it sees is n data points. It sees an embedding z and a corresponding label, and then another z, another label. It sees exactly n of these. And it needs to learn its parameter matrix, which is gamma, which has size d squared. So it has n data points, and it's taking these n data points and it's fitting d squared parameters. So this tau is sort of describing the machine view, right? It doesn't have these smart interpretations of, oh, we need to decorrelate tasks from tokens, and to do this, we need to predict the token distribution and the task distribution. These are both linear covariance estimation problems. These are all the nice, interesting descriptions. The machine description is just, I need to fit d squared parameters and I have n data points. But each of these will play a different part in the story. So these are our main scaling limits. And we're going to consider our results in the regime where these are all scaled proportionally as dimension goes to infinity. Cool. Now with this, we're going to find some deterministic equivalent for the various test errors. So again, we have two test errors. One was the true in-context learning test, where I sample a new prompt with different tokens and a fresh task from the true task distribution. So that was this guy. And I'm also going to compute the in-distribution error, where I sample new tokens, but I sample the same task from my finite size tasks, k length tasks. So these are both going to be random quantities in the sense that for a given finite sample of pre-training data, I'll learn some parameters. I'll learn this gamma under my MSE loss with ridge. But that will depend on the randomness that comes from my given finite size sampling of my pre-training data. And then I can study the performance of that particular instance of a parameter on a particular instance of my testing data, but that will still be a random quantity. So if we want to look at the typical performance of these trained parameters, which have been trained on a typical batch of finite size pre-training data, and tested on a typical batch of testing data, we need to do some averaging. And that's what I mean by deterministic equivalent, right? The error that we actually want to capture is random, but we can study its typical behavior particularly in this large dimensional limit. So I'll flash a formula. This is one of the main formulas of the work. All that this is just basically saying exactly what I've said. So we define all of these, messy, where's my pen? Yeah, we define all of these sort of messy, definitions. This is some Stieltjes transform thing, lots of random matrix things going on. But we define, all of this mathematics, and this is our data-informed quantity. So again, we're talking about finite sample. We have a finite sample formula, right? I have finite pre-training data. I'm testing on some instantiation of my testing distribution. These are random quantities. Go ahead.
One small question, just because like I guess my context length in my head is not long enough. What is rho again? I forget. Sorry.
Sorry, yeah, rho is the label noise.
Oh,
So
right,
just think
right.
about it as something close to zero.
Cool, cool.
Yeah, this is kind of
Thanks.
like a little signal to noise ratio thing that shows
Hmm.
up.
That makes sense. Cool.
But yeah, so again, this is a random quantity. This should really be approximately equal to, um, like asymptotically equal to. So this is a random quantity, which again comes from the randomness in the parameters, which comes from the randomness in our pre-training data. But when we study its typical performance, we want, we want this thing to be self-averaging in a high dimensional limit, and we want that average to make sense. And we have a formula for that average. This is the average performance for a given finite sample of pre-training data on a given test task. And yeah, this is kind of a messy formula. The one thing that I will highlight about it, which we'll talk about briefly later, is that it's very evident just from the structure of this formula that there will be some kind of double descent phenomena. Because you notice that this formula is piecewise in terms of this variable tau. Again, tau is the scaling parameter for the number of contexts. So tau is just number of contexts, effectively. And we see that there's already going to be some strange sort of piecewise behavior that happens whether or not tau is less than one or tau is greater than one. So we'll see this soon, but yeah, that's the most obvious thing from this formula. And then similarly, we can look at the second test error that we wanted to look at, which was this training error, this in-distribution error. And this will have a similar structure, right? So again, we can already see that there's going to be some piecewise behavior in terms of tau. And again, this is just a formula. I just wanted to flash it for completeness, but yeah, everything, there's no dimensionality anywhere in here. So D does not play, the dimension of the tokens and the dimension of the tasks does not show up in this formula at all. This formula is completely dependent on the three parameters that we've identified and rho. So label noise, and then our three scaling variables, and that's it. Cool. So yeah, flash the formulas, and then what's, okay, so
Wait, can I ask one small question too? I was gonna
yeah, of
wait till the
course.
end, but um, yeah. So at least in I guess the same thing for the previous one, but you mentioned like these things hold asymptotically as like asymptotically. But what do you mean? So you mean like you're also taking the limit as d tends to infinity also, right? Okay,
Yeah,
okay, okay. Yeah, that's what I thought.
yeah. So
Does the yeah.
sorry.
No, does the order like matter? I don't know. Like or no?
This is interesting. So I have a slide which I'll briefly discuss in a bit that these limits are sometimes a little strange.
Hmm.
But for most of the stories that we've identified here, these limits do commute,
Okay,
or
that's
there's,
interesting.
there's a sensible way of taking the limit. In particular, we're specifically taking a proportional limit. So we're
Hmm.
not taking d to infinity and then context length to infinity,
Hmm.
or context
Hmm.
length to infinity and
I
then
see.
d to infinity, because that would be slightly weird, right? Like you get
Yeah.
pushed into different, not weird, but just it's a different phenomena.
Yeah, yeah, yeah,
Different
of
things.
course. Yeah.
So we're explicitly taking like this controlled proportional limit where yes, dimension is large, but dimension is only large as the number of contexts.
Okay. So it's
Or
similar in
sorry,
spirit. Yeah, so it's like somehow it's similar in spirit to like this my Montanari stuff, I guess, right?
precisely.
Cool.
Yeah.
Yeah. I thought so, but different.
And then yeah,
Cool.
the
Cool.
point is that like for not for every quantity, like we're not so lucky all the time, but for this quantity, this typical error appears to be a self-averaging quantity. So what that means is that looking at finite dimension and taking the average behaves the same as just looking at one sample of it and taking the limit to infinity. Like the variance decreases with the correct, rate as you take dimension to infinity. The quantity becomes more stable and it concentrates around its average. So in some sense, finite sample averaging, like finite sample ensembling, is the same thing as just limiting dimension to infinity in the correct limit. These two things behave the same. And these are called self-averaging quantities, and they're super nice because it means that we have more tools for studying them. We can look at the large dimension proportional limit, if that's convenient analytically or empirically, or we could just take an average. But they behave similarly. And yeah, this is the key for our derivation. So again, we define these parameters gamma star, and this is just going to be the minimizer of this MSE loss between the true label and this predictor label with the structure, the inner product of gamma by h. And then we have some ridge term. And we can actually just directly write down what the solution of this is going to be. It's going to have this nice sort of resolvent looking structure. So if I were to just take the form of gamma star as an argmin problem and actually do the argminning, I would get this exact predictor. And this is written in terms of a sum over all my n samples of my embedding h of z and my label. And we see that like this has a very when we see something like this, it's very exciting. It has some nice structure because we see like, okay, this is just some slightly looks like ridge regression. So we can study it with very similar tools. And that's exactly what we do, right? So again, we have this resolvent term and then we have these label features, and this looks almost exactly like the finite sample structure of ridge regression, just with much more complicated features, more complicated covariances. And so what we do is we take the structure of these, like this is exactly what the trained model will learn under our assumptions. And we can average over the randomness in the tokens, as well as the randomness in the label noise, the rho. And we'll get we'll get some formula in terms of the tasks. And then we can average over the tasks. We do this separately because the statistics of the tasks are more complicated because we've chosen only finitely many of them. So we're gonna have some like weird finite size effects. But at the end of the day, what we get is we have a deterministic equivalent for these parameters. So again, if I were to train an average network of this structure with an average finite sample of my pre-training data, it won't be these parameters. But the typical parameters will behave like these parameters. And those parameters that I'm talking about have this form. So it's going to look exactly like this inverse covariance plus ridge times the covariance. And what is this RTR term? This is literally just the sample covariance of my tasks. So again, I have k tasks. This is my sample covariance. This is my sample mean. And this is some renormalized ridge. So we see that, yeah, this has the exact same structure as previously. It's just in a deterministic form. The first thing is in a random form. The second thing is in a deterministic form. And this resolvent becomes like this covariance with a renormalized ridge. And this feature, the red term, becomes a different covariance of the tasks. And then, yeah, we can write this resolved ridge in terms of just asymptotic properties that we have, or asymptotic scaling variables. So yeah, like I haven't gone into a lot of detail for the derivation because time purposes, but the main point is that it kind of is just ridge regression. It's just a lot more involved. But all the same insights remain, right? It's like at the end of the day, you have some sample, you have some finite sample, you're trying to estimate the finite sample covariance of your tasks. This introduces, some noise threshold, you resolve the ridge of your problem, you end up with some Stieltjes transform, you look at the resolvents. Very, very nice standard ridge regression. That's the intuition. But yeah, if we have more time at the end, I'd love to talk more about the computation. Cool. So yeah, that's the meat of it. What can we actually say? So, at the end of the day, we do theory for fun, but we also do theory to say things about the world. So, what can we say? We have these big, messy formulas that are interesting to look at, but the point is that they should tell us something. So, the first thing that they tell us very blatantly is there's these piecewise structure that happens in tau. Again, tau is one of our three scaling variables. So, tau is controlling this proportional quadratic interaction between the number of contexts, the number of prompts, and d squared. And we see that if we just plot, so I'll focus first on this curve. Sorry, I should have drawn these separately. But yeah, let's focus first on this curve. So this is a curve of my in-context learning error against tau, which is again my context divided by d squared. And this is tau equals 1, which is where my piecewise discontinuity happens in my formula very explicitly. And this is just a plot of my formula overlaid with actual finite sample simulations where I actually solve for the parameters and I compute their error. So these have some noise because, again, there's going to be fluctuations that come from the fact that there are finite sample effects with the pre-training data. But as you can see, not only does the finite simulations, these dots, fit the curve pretty well, we also explicitly see this double descent phenomena happening. Do you have a question?
Yes. Yes, there is one question. That was my opener, but yeah. So like the colored lines on like on either plot, like should I also think that the dimensions being the same? Like for example, is like the blue, like when alpha is 100 is like the 80 kind of thing in the first plot. Like what is the actual,
Ah,
you
yes.
know?
Yeah. So I'm playing a bit fast and loose with, the equivalence of the theory and the experiment.
Mm.
So in this case, so I'll talk about this plot later. This is a different setting.
Yeah, yeah,
But in
sure.
this setting, I actually take dimension the same. So each of these have the same dimension. This
Okay,
plot was dimension equals 100. And
okay.
again, I know I gave this long spiel about how the theory is only valid, with
No, 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 that's
dimension.
fine. Mm.
So what this means is that I'm taking my context length to be 1 times the
Mm-hmm.
dimension. And this
Mm-hmm.
is 10 times the dimension. This is 100 times the dimension.
Mm-hmm.
So the context length is still scaling with the dimension.
Yeah.
The alpha is not, if that
Mm-hmm.
makes sense.
Yeah.
And also like it's one of those design choices where, I make this plot for d equals 30 and it looks horrible. I make it for d equals 50, it looks a lot better. I make it for d equals 100, the finite samples dots are effectively right on top of the curve, right? So there's some finite sample effects that happen, but empirically,
Mm-hmm.
the larger I make my dimension while I can still run it without memory issues, the closer it gets to my theory curve,
That
which
makes
is
sense.
precisely the
Yeah.
point. Yeah.
Yeah, the reason I ask is because maybe I'll ask one of my my questions for now, I guess. I guess one of the main questions I had was basically this was like in the finite dimensional case, like how far, like, can you quantify how far you are from the actual limiting case? At least empirically, it seems like pretty close.
Yeah,
Mm,
empirically, yes. I haven't looked at it analytically. In terms of best practice, like what I found when I'm running these simulations is that d equals 100 for the linear model is a pretty good surrogate for the asymptotic theory.
and that's
And there's
pretty,
also,
yeah.
yeah, which is like it's runnable, And like there's also things that you have to consider where like the formula that I'm plotting here is actually the ridgeless limit. So I'm taking ridge to 0.
Mm,
But when
hmm.
I'm computing my actual, like these dots, when I'm actually solving, the least squares minimization, um, I want some finite ridge so I don't have
Yeah,
numerical instabilities. So there's always going to be a bit of like a tug of war where you're playing with parameters. But yeah, in general, for the linear model, I think d equals 100 is pretty good. And
that's
for the
yeah.
nonlinear models, maybe d equals 80 is
Really.
sufficient.
I mean, that's pretty, to be honest, that's pretty fast convergence because 100 is pretty finite, to be
Yeah,
honest.
yeah, no,
Okay,
exactly.
that's
Yeah.
cool. That's cool.
Yeah, I mean, yeah, I'll talk more towards the end if there's time about
Hmm.
like extensions that I'm working on. But
Yeah.
yeah, I think this is honestly a feature of the fact that we're working with super nice data.
Hmm. Yeah,
Like
yeah, yeah, yeah.
everything's
I was gonna ask that.
isotropic in this case. Yeah. And so everything is like all of the self-averaging quantities in this problem self-average very quickly.
Hmm.
If
I
I
see.
were to
I
look
see.
at slightly more realistic but less well-behaved data, for example, power law data,
Hmm.
All of the quantities that I want to self-average do it
Slower.
slower.
Okay, that's
So
cool.
like this, I think this is a feature of the fact that we've chosen really nice data. So yeah.
Cool.
Um, but yeah, so this plot shows that my theory curves match my numerical simulations, and we also see a double descent. So this double descent occurs in the variable that controls the number of contexts divided by the dimension squared. And so this is giving us some indication that there's, like a problem complexity and an algorithm complexity, right? The problem complexity is going to be dependent on n, and the algorithm complexity is going to be dependent on d squared or something, and we're going to transition from the overparameterized regime from underparameterized to overparameterized. Cool. And then yeah, this plot is slightly different. So this plot was done, this was done with literally just my reduced parameter linear attention. This is not only a toy model, but a reduced parameter toy model. This is just learning gamma, the gamma matrix, which again is some subset of the attention in the value matrix. This is a network that I actually trained. So this is like an actual nonlinear network. It had some structure with like a softmax, attention, followed by an MLP with some residual connections, one block of that, and then another block, and then another block. This was like a three-layer block MLP res connection attention network. And what I've done is I've plotted still the same tau, and I also see some kind of double descent behavior. And what I'm doing is I'm doing a sanity check because at the end of the day, obviously these curves are not going to match these curves because they're very different architectures. But I want to make sure that my theory is somewhat consistent, and for it to be consistent, I need dimensionality to not matter. Because this is a dimensionless theory, so this should behave approximately dimensionless if my theory is a good descriptor. So that's why here alpha is fixed, like here I'm varying the context length, but here I fix the context length and I'm just actually varying the dimension. So context length is scaling proportionally to this dimension. Here my context length is 20, and then it's 40, and then it's 80. But the big thing to note is that I'm controlling for the dimension as my primary variable. And yeah, it's not a perfect match, but we can see that more or less these error curves are pretty consistent in dimension. And further, as I limit the dimension higher and higher, I get pretty much exactly my predicted double descent at tau equals 1. Over here, there's some finite sample effects, right? It's like the peak of this interpolation threshold is happening slightly above 1 or whatever. There's some noise. But as I take dimension larger and larger, my interpolation threshold happens pretty much exactly at 1, which is promising.
I have just one more small question. Um, yeah, is this just like a numerical like blip or something? But what or like why do you expect? Do you expect that there's like a monotone? I say bless you. How to say like so your double descent starts at different points, and like I imagined like that point would kind of just keep shifting towards one from the left to the right. Like, do you know why there's like an oscillation kind of thing, or is it like a numerical thing? Like first, you know, and
Yeah, I think I honestly think it's maybe numerical.
Mhm.
Um, as in, sorry, I don't necessarily think it's numerical, but I
Okay,
think that that's reasonable. Just
okay,
because there's a lot going on under the hood
yeah,
that kind of mars the interpretation of this plot. For example, as I'm increasing dimension, how do I scale my ridge? How do I scale my regularization? How do I scale my batch size? How do I scale my number of epochs? Like there's all of these engineering things that when you're thinking
hmm
about asymptotic theory and
yeah, that's
studying the
fair.
asymptotics of something, it becomes hard to predict how other things that you don't have to worry about in the theory should scale. Right? There may be some optimal scaling of epochs or batch size or ridge or whatever that depends on dimension. I
hmm
haven't figured
hmm
it out yet, but I think that, like, if I had to guess, I think that's the biggest contributor for why
That's fair.
these things are behaving a little weird. Yeah.
Also, there's
But
like
also, oh
there's like
yeah,
some
in the
chat
chat.
question.
Yes, data is still isotropic Gaussian, so the entire data selection for everything is the exact same. The only thing that changed in this right-hand side plot is the architecture.
Yeah, that makes sense. Cool.
Cool. Now let me erase everything. And then, yeah, one final plot while we're here is basically just saying the same thing, but on a log-log scale plot. So
Hmm.
what I've done here is I've plotted token dimension on the x-axis and the number of contexts on the y-axis. And my point for this plot is that this is the linear theory. So this is my quadratic scaling. This is just the line n equals d squared on this log-log plot.
Mm.
And when I'm plotting these dots correspond to different architectures at different dimensions and the location of the interpolation threshold. So sometimes it's slightly above 1 times the dimension, sometimes it's exactly, sorry, dimension squared. Sometimes it's like slightly like 1.2 times dimension squared, sometimes it's like, 1.05 dimension squared. I'm just plotting the location as determined numerically from the error curve of these ISL tasks at different dimensions for different architectures. And what you can kind of see is that, yes, the intercepts of these lines, so the scaling, the constant in front of this d squared is changing with architecture, but the d squared is not changing. So my hypothesis here is that pretty much as I add more layers, more blocks of softmax MLPs, I'm pretty much just scaling these lines, or sorry, I'm scaling this polynomial n equals number of blocks times d squared. That's my hypothesis. This isn't proven, but like that's empirically what seems to be happening. So as I make my architecture much, much deeper, more expressive, it does scale the location of this, but it doesn't scale the proportionality. We still have d squared proportionality, which is cool, right? Because this was derived from a linear theory, so it's nice to see that this remains. Yeah. So yeah, this is the first story. We have a double descent and some nice, quadratic scaling sample complexity. There is another story that I wanted to mention in terms of context length, but given that we only have 7 minutes left, I think I'll probably skip this because I think the final story is more interesting, if that's all right with everyone.
Yeah.
So this would just like, again, we have these three parameters. We have tau. I talked about tau, that's the double descent. Alpha is the parameter that determines context length.
Mhm.
There's some non-monotonicity, limit, interchange, commutativity stuff that we could talk about here, but again, in the interest of time, I'll go to kappa. So kappa is interesting to me because again, it determines data quality.
Mhm.
That's the only reason why we introduce it into this theory is because we want to limit the pre-training data quality. Sure, there's n contexts, but you only actually see k unique functions. And again, kappa is the scaling k divided by d. So it's this proportional scaling variable for the number of unique tasks that I see during pre-training, and it's a measure of pre-training data quality. And the reason why this is interesting is because there was some paper recently by Raventos and Suri Ganguly talking about what is the actual inductive bias of a transformer when it's doing some regression task. Is it Bayes optimal? What's its prior? What's the actual algorithm under the hood? And they make some argument for studying this empirically by comparing the performance of their pre-trained transformer, which is this orange curve, to two different Bayesian estimators. This blue Bayesian estimator is just ridge regression. They're just doing optimal ridge regression on each context. So it's not really an in-context learner.
Mhm.
It's you're just showing the thing exactly one context and you're like, do ridge regression on this, do optimal ridge right now. And it'll do it, and you'll get a nice, flat, super low error. Then they also compare it to this discrete minimum mean squared error estimator. I just call this the memorization prior, or the
Mhm.
discrete prior. So again, you're only seeing one context. You're not really looking at like, multiple contexts, true in context learning. You're just seeing one context, and I tell you the true function that is giving this context is one of the k, W1 through WK. Pick the closest one.
Mhm.
So your prior is that the
Mhm.
function that you're seeing in the current context is determined by one of these W's. And all you have to do is pick the closest one. So you're doing some, non-parametric kernel estimator. Cool. And then there's the transformer model. And their argument is as they compare the number of pre-training tasks, so this would be equivalent to my k with some scaling, and the in-context learning error, they see that for a low number of pre-training tasks, again, 2 to the 8th is not necessarily low, but like for a low number of pre-training tasks, this pre-trained transformer behaves very similarly to the discrete estimator. And then later, past a certain threshold, maybe here, as I give it more unique pre-training tasks,
Mm.
better representative of my true function distribution, it starts behaving a bit more like the Bayes optimal ridge estimator. And again, like, it's hard to make mechanistic claims here, right? It's like all we're looking at is we're looking at comparing error of our thing with error of two different things, right? And we want to be able to hopefully make some mechanistic conclusion, right? So what's the best way to do that? We want to be able to actually say, is this thing memorizing and then generalizing, or is this just numerics, right? So we want to be able to say something like this. And the thing that's I'll try to rush through this, that way I don't keep people here too long. But the thing that's inspired the way that we approach this problem is let's just look at the structure of the ridge estimator. So this is just a ridge estimator on a single context. All it sees in terms of the task that it's trying to predict is this label y. And it's just doing ridge regression on this label. Or sorry, on this sequence, right? It's determined by this label. It doesn't care if this label is generated, so again, this label yi is going to come from some w dotted with xi. It doesn't care if that w is drawn from our true in-context learning full generality test distribution, or if it's drawn from the training set of finite size in distribution generalization distribution, right? It doesn't care. All it sees is this label. All the ridge predictor is ever going to do is do ridge regression. It doesn't care where that feature came from. So the error from this ridge estimator is going to be exactly the same on the IDG task as it is on the ICL task. In some sense, it's a perfect generalizer.
Mhm.
I'm speaking very schematically here, but if there was any discrepancy between its performance on the IDG, the training tasks, and the ICL, the testing tasks, then in some sense, the training tasks mattered to the estimator, and there's some notion of memorization happening. But if there's no discrepancy between these two errors, between these two testing regimes, then in the same sense, the training tasks don't matter at all.
Mm.
And this estimator is just generalizing. And at the end of the day, that's what I want to like answer from in context learning, right? How do we know if a method is actually generalizing over the function space? Like usually in machine learning, we think about generalizing over token space, but how do we think about generalizing over this bigger function space? And I think this question, like it's a toy question, but it kind of gets at that, right? And the framework that we use to study this is we're going to define some simple quantity. We're just going to call this a measure of task generalization, generalizing over function space. And we're going to subtract the
Mm.
training distribution error from the true in context learning distribution error. And again, the intuition for this is when we look back at our ridge regressor, this will be 0.
Mm.
What do we conclude from that? It's a generalizer, right? It doesn't care anything about the pre-training distribution. It doesn't care that the pre-training distribution had finite samples. It just cares about the one task at hand. It's a
Mhm.
generalizer. So when this is large, that means that there's a large discrepancy between this IDG error and this ICL error, and the model is more likely to be memorizing. It's more likely to be conditioning on some specific information in the training distribution that's giving it low IDG compared to higher ICL. And conversely, if this is low or if it's 0, then these are basically the same, and there's not much extra information you get from knowing the training distribution as opposed to just testing on a general task. So we think that like smaller g is a good measure for true task generalization. Is the model actually learning the true distribution? And this is slightly complicated by the fact that if I have excuse me, if I have k samples from my Gaussian and k is going to infinity, eventually the
Mhm.
distribution of k samples over a Gaussian will just limit to the Gaussian as k goes to infinity. So as I take k to infinity, g will always limit to 0. The question is, how quickly does this happen?
Mhm.
And that's exactly what I'm plotting here. So the first plot, the left-hand plot, is a log-log scale, and the right-hand plot is a log-linear scale. They're basically exactly the same. The only difference, or say, yeah, the difference is the scaling. But I'll focus on this plot because I think it's the clearest. So what am I plotting here? These are different versions of my theory curve. And by theory curve, I mean my theoretical result for ICL error minus my theoretical result for IDG error. So it's this G task variable that I'm learning. And I see that these decay towards 0. Obviously, they have to decay because the distributions limit to each other as k goes to infinity. But it decays very quickly. Compare that to this discrete prior, which again, this is the pure memorization prior. This is just choosing a task vector conditioned on the fact that it has to be one of these k task vectors. And we see that this is decreasing at pretty much like a very dimensionally cursed rate. This is super logarithmic.
Mhm.
And this is linear decay.
Mhm.
Or sorry, one over kappa. So the point is, there's a lot more I could say here, but we're well over time. Just to wrap this up, the point is there's an interesting trade-off that happens between memorization and true task, true function generalization. And we think the best way to study it is by looking at this difference between the ICL performance and the in-distribution performance. If this is 0, the model is a generalizer. If
Mhm.
this is large, the model is a memorizer. And we can also look at the rate at which this decreases towards 0 as I give you better quality pre-training data, as I give you more function samples during your pre-training data. How does this decay? And we see that there's a nice phase transition that happens around
Yeah.
kappa equals 1, which is when I have equal token dimension and equal number of pre-training tasks. And this is, again, this is a much better inductive bias. Like the conclusion here is that this transformer has a much better inductive bias than the uh, discrete estimator, this memorization prior, which is decaying super, super slowly. It's not using the pre-training data quality efficiently at all, because it's just guessing over the training set. And yeah, this is all like all of these curves look pretty much exactly the same in the empirical case. Like if I do some plot of, I don't have it here, but yeah, if I do my plot of my pre-trained transformer with like, super nonlinear, 3 blocks, 3 layers, MLPs, res connection, softmax attention, I'll get a curve that looks exactly like this,
That's cool.
uh, which is nice. Yeah. So yeah, just to wrap up, I guess, not to rush too much, but there's a lot more we can do here. Some of it I've already started doing. So yeah, we can add a lot of structure into this problem. We can add particularly general task covariance,
Mhm.
and we can start looking at like different exciting interplays between the structure of the tasks at pre-training time versus testing time. So this is something that I'm currently working on. And then, yeah, something that I hope to think about more is that how nonlinear can we make this problem? Because
Mhm.
linear attention is a very nice playground analytically. So can we push this to quadratic features? Can we push this to single index models? How far can we take this and still understand like exactly end to end what the model is learning? Yeah. Thank you
Cool.
very much.
Thanks a lot, actually. So it was really nice talk. I mean, I asked one question. I think other questions somehow that I had written down you asked while talking, or you answered while talking. That's great. So I quickly ask everyone if they have a question in the audience. Right, there is something written. Okay, it's a compliment. That's good. That's also good. Okay. So maybe I have just I have this like one like high level question, which is probably influenced by low blood sugar at the moment or something. Um, right. So here I guess like the you talked about like this data quality. So this kind of trade-off between I guess K and N in some way, or kappa. Um, right. And so my question was like, if the tasks were generated in some more nonlinear way,
Mm.
should I think of like K somehow? I don't know. Like, should this be somehow be related to like the metric entropy of like the support of like where my tasks are coming from, like in this function space? Because like somehow you have these like finite dimensional, like really nice behavior. But what if it was like some best of class, something crazy like this? Like, would K scale very slowly?
That's a good question. This I'm not 100% sure off the top of my head, although there will be, I know that there's going to be some scaling in the problem that comes from like the information exponent of the functions that you're studying. I just
Hmm.
know this because I think Denny Wu at Flatiron is studying something similar, like some in-context learning for polynomials. And he does like a similar program of research where like, we can say something like in context learning is implementing one-step gradient descent or two-step gradient descent, right?
Okay.
What's the complexity? And I think
Hmm.
if I remember correctly, his result is something like the key scaling quantity will be the dimension raised to the information exponent of my polynomial.
That's
So
interesting.
in here, my polynomial is linear, so this is 1. If I
Hmm.
were going to look at purely
Hmm.
quadratics, it would
I
be
see.
2. I do not remember if this was his task diversity or his context length. I believe
Hmm.
it's context length. And the reason for that is like if I get rid of the in context learning like feature of this sort of thing, and I just think about doing polynomial regression, I'm going to want if I'm doing quadratic regression, I'm gonna want d squared samples.
Hmm.
So I think the scaling that's gonna happen is gonna be context length. At least this is the one that I know of. In
Okay.
terms of task diversity or data quality, I'm not yet sure. Um, yeah, this in some sense is going to depend on the geometry of the function space, which
Yeah.
here is isomorphic to RD. So it's
Exactly.
very,
Yeah. Cool. That's
but
interesting.
for complicated functions, I don't know what the correct metric would be on that.
No, that's really interesting. Yeah.
It also it depends a lot on your distribution. Like,
Obviously. Yeah. Yeah. That's
so
interesting.
Gaussian, I don't know. Yeah.
I had some other questions, but same thing. I guess you can also ask many questions. Um,
Lots of
like
questions to ask. Yeah, it's
yeah,
fun.
it's interesting. So it's very cool. So if no one has any other questions, I'll save mine for I guess next conference or something. Yeah, but it was a pleasure. It was a nice talk, and wait, let
Yeah.
me just.